Hi, hello friends. Welcome to my YouTube channel. Now, in this session, I would like to share the solutions of Assistant Engineer Electrical of APTransco AE 2017 paper. The first question on the screen is the main purpose of using core in a transformer is to. Normally, transformer will have two windings. The first one is primary winding and the second one is secondary winding. When the current flows through these windings, it will create a magnetic lines of force like this, that is flux lines, and because of the load also there is a flux lines flowing like this. Okay, so in order to increase the lines of force, we will use the core material in between them like this. Okay, so core is used to increase the flux lines, or we can say decrease the reluctance. Okay, so the suitable answer for this question is C, reduce the reluctance of the common magnetic circuit. And the next question, is a 220 volts separately excited DC motor takes 20 amps current and having armature resistance of 1.0 ohms. A 220 volts, that is 220 volts DC motor with a armature resistance of 1.0 ohms, and it takes a current of 20 amperes, and the armature constant Ka phi is 1.5 radians per second. And what we need to find here is speed, and the speed is in RPM. Okay, and the formula is EB, that's a back EMF, is equal to V minus Ia into Ra, that is equal to 220 minus 1.0, that is armature resistance, and armature current is 20. We will get 200 volts as EB. Okay, and we know the relationship between the EB and speed is, so back EMF is equal to, that's armature constant Ka into phi into W. So this is speed in radians per second, but the given solution is in RPM, so we will convert this. Okay, so next here, so EB is nothing but 200 volts is equal to the armature constant K into phi is nothing but 1.5 into W. That implies, so 200 divided by 1.5 is equal to, so 2 pi n divided by 60. That implies n is equal to 4000 by pi RPM, and the solution is D here. And next, third question here, a three-phase slip ring induction motor, the slip at some speed is 0.05. The speed is reduced by inserting an external resistance in the rotor circuit, and the slip is 0.15. If the rotor winding resistance per phase is 0.2, the external resistance is. So for this problem, the first slip at some speed is equal to 0.05, and slip at some other speed is S2 is equal to 0.15. Okay, well, normally we know that S1 is proportional to R1, and here S2 is proportional to R2 here. Okay, so R2 is nothing but what we have done here. So R2 is nothing but previously we have some resistance, that is R1, and to that we are adding some external resistance Re here. Okay, from this, so S2 by S1 is equal to R1 plus Re divided by R1. So we know the value of R1. So what is the R1 here? So R1 is nothing but 0.2 ohms. Okay, so from this S2 is nothing but 0.15 divided by 0.5 is equal to R1 is nothing but 0.2 plus external resistance RE divided by 0.2. So by solving this equation we will get RE as 0.4 ohms, 0.4, and the answer is C here. The next question here, when VV or open delta three-phase transformer system is converted into delta delta system, the increase in capacity of the system is. Normally when we have delta delta system is getting converted into open delta system. Suppose for example say the delta delta system will have 100 kVA capacity. When one winding is open circuited, then we will have 57.73 kVA is the winding is the capacity of this open delta winding. That means this much of capacity is decreased because of when we open the one winding. So now here the given question is, suppose this is 100 kVA and how much will be this increase in capacity. So we have to represent it in terms of in percentages. So normally for example say I will take X kVA here. Okay, so by cross multiplication here X kVA is equal to, so 100 into 100 divided by 57.73, we will get 173.22 kVA. Okay, if you observe here how much capacity is increased here is, so this value is 173.22 kVA. That means there is a increase of 73.2 percentage of capacity. So the answer is D here. And the next question is, 3 kilowatt load is supplied by auto transformer with a 0.7 transformation ratio. That is, they have mentioned K value. Conductively transferred power from primary to secondary winding. So we will substitute the direct formula. The power transformed by conductively is equal to, that is K into, so power rating of two-phase transformer, that is equal to 0.7 into 3 kilowatts, that is nothing but you will get 2.1 kilowatts, and the answer to this question is A. And the next question here is the sixth question. The number of commutator bars for a 4-pole 2-layer DC lap winding with 24 slots and one conductor per layer is. And the solution for this problem is, normally the commutator bars is equal to commutator bars or segments is equal to number of coils. That means one coil will have two sides like this. So this is a coil side 1 and a coil side 2 here like this. Okay, here we have commutator bars like this. Normally in the given question we have 24 slots. Okay, so I will take the slot like this. In this slot it's a double layer winding. That means we will have two conductors, first conductor and second conductor. So here these two are nothing but conductors. Okay, so these two conductors will make one coil. That means 24 slots will make 24 coils. That's nothing but 24 commutator bars or segments. And the solution for this problem is B. Now the next question, the torque developed by any three-phase induction motor at 0.8 per unit slip is. So in the given question, the slip is given as 0.8 per unit. Normally, from the speed torque characteristics of induction motor, we can observe that like this. So here we'll have slip is maximum and slip is minimum here, and the rotor speed is going to be 0 here, and here rotor speed is equal to synchronous speed here. The characteristics will looks like this, okay, approximately. So here up to this point, this region will called as low slip region, where the characteristics are similar to linear characteristics. Okay, as a slip value increases, we will have this one as unstable region, and here we have stable region. Okay, as the slip value increases, we will get a unstable region. So here we have unstable torque produced because of slip is 0.8. Suppose if the slip is say 0.2, then we can say it's a stable region. And the next question on the screen is 8th one. The EB by V, that is a back EMF by supply voltage, is a ratio of DC motor, is an indication of is dash. So normally efficiency is given by output power divided by input power. So here we have output is nothing but we will take the electrical equivalent of mechanical power. So electrical equivalent of mechanical power. Why? Because it's a motor, and divided by, and supply is electrical power, that is electrical power. Okay, so by neglecting the losses, we can write this equation as EB into armature current IA divided by V into IA. So if IA gets cancelled, this is nothing but EB by V indicates the efficiency of the DC motor. Suppose if they asked for V by EB, it will indicate the efficiency of generator. Okay, just like ulta. And the next question here we have is, which of the following test is usually conducted to determine the efficiency of traction motors? So in traction, generally we'll use two types of motors. Traction, first we will use three-phase induction motors, and second one we will use DC motors. In that one also DC series motors. Now in this case, in the given options, we need to find the efficiency of DC series motor. Okay, except the field test, the Swinburne's test, retardation test, and the Hopkinson test are used to find the efficiencies of DC shunt motors and compound motors. Okay, the only option that we left is field test. So field test is a test used to find the efficiency of DC series motors here, that is a traction motors. And the next question here, an 8-pole 50 Hz 3-phase induction motor is running at 705 rpm. So this speed is the rotor speed and has a copper losses of 5 kilowatts, and its rotor input is, first of all, what is the synchronous speed of this induction motor? Ns is equal to 120 F by P, which is equal to, so 120, the given frequency is 50 Hz divided by how many number of poles? 8 poles. This is equal to 750 rpm. Okay, the formula here is the power input to the rotor divided by the power copper losses is equal to 1 by S. So slip is nothing but Ns minus Nr divided by ns, that is equal to 750 minus 705 divided by 750. This is equal to, by solving this we will get 3 by 50 here, and we need to find the rotor input. So power input is equal to, so 1 by s means 50 divided by 3 into the power copper losses is 5 kilowatts. By solving this you will get 83.33 kilowatts. And the next question is, a 3-phase 4-pole 50 Hz induction motor runs at a speed of 1440 rpm. This is the rotating field produced by the rotor rotates at a speed of dash rpm with respect to the stator field. Okay, so what is the synchronous speed here? That is ns is equal to, so 120 f by p, you will get approximately 1500 rpm. Okay, both the fields rotate at synchronous speeds. Okay, so this rotating field rotates at synchronous speed of 1500 rpm and with respect to stator field. So stator field also rotates at a speed of 1500 rpm. Okay, so when we compare these two, they are rotating with respect to each other with a speed of 0 rpm. Why? Because both the fields rotate at synchronous speed only, so they are at 1500 rpm only. With respect to each other means it is going to be 0. Okay, so because fields. Next question. And the next question, generally crawling in squirrel cage induction motor is a tendency to run stably at a speeds as low as, it is nothing but 1 by 7th of the synchronous speed. Suppose if they ask for cogging is nothing but magnetic locking here, so it is going to be happen at a synchronous speed of 5th. Okay, and crawling at 1 by 7th of the synchronous speed here. Okay, and the next question, it's a very simple question. The starting torque of capacitor start induction motor is directly related to the angle theta between its winding currents by the relationship. So the direct relationship is T is proportional to the phi 1 phi 2 into sine theta, where theta is the angle between these fluxes phi 1 and phi 2 here, and the answer is B here. And next question, the fractional pitch used for eliminating 7th harmonic from the EMF wave of an alternator is, the formula for this one is, the fractional pitch used for eliminating the nth harmonic is equal to, so n minus 1 divided by n into pole pitch. Okay, so normally it will be taken as a 180 degrees electrical, so which is equal to, so 7th harmonic means 7 minus 1 divided by 7, this is equal to 6 by 7, and the answer for this case is D. And here for the 15th problem, I am not able to solve this problem. If you know anybody solution of this problem, please share. And the answer for this problem is it is D, 24.9 seconds. And the next question, and this question here in 16th one, while keeping the excitation constant, if the steam excitation constant here means the kVAR is constant, if the steam supply of an alternator running in parallel with another identical alternator is increased, that means steam supply is increased of one alternator, so which will cause us increase in kilowatt, that is power supplied by the machine will increase here. Okay, there will be no change in kVAR consumed here. That means it is the portion of the share in the load will increase. Why? Because of there is a direct increase in kilowatt hours. Okay, suppose if you want to increase the reactive power, so reactive power if you have to increase means you have to increase the excitation. Okay, that is the key here. And the next question on screen is the effect of increase in the load on a synchronous motor running with normal excitation is. Okay, if we observe the V curves and inverted V curves of synchronous machine, so on the x-axis we will take excitation, and on y-axis we will take the power factor and the armature current here, like this. Okay, now here, so this is going to be the power factor curve, and this is going to be our armature current. I'm just drawing roughly here. So here we have normal excitation, and the last we have under excitation, and here we have over excitation here. Okay, what is happening here? If there is a effect of increasing load, that means simply we are increasing the IA load on the synchronous motor while running with normal excitation. So normal excitation is somewhere here. So normal excitation is here. Okay, here we are increasing the current value. What about the power factor? So power factor, you can observe it is going to be decreased like this. So the option here is the current IA increases but decrease in power factor. So from these curves. And the next question, the transmission lines are transposed to reduce. Normally on the ideal configuration is like this. The transmission lines are kept like this configuration. So R, Y and B. They are normally transposed, means like this manner, like this, and they will interchange like this. Okay, so in this manner they will transpose. So transposing of lines. Okay, so this transposition is done to avoid the or reduce the interfacing with the neighboring communication lines. Why? Because in normally in transmission lines we will use the conductors like this, and also we will use the same tower for communication lines also. So this is for communication and this is for power lines. Okay, so in order to avoid the interference with the neighbor communication lines, we will transpose the conductors. Okay, and the next question here is, if the base current and base voltage of a 345 kV system are, this is nothing but 3000 is nothing but this is the base current and this is the base voltage of a 345 kV line respectively, the per unit voltage and the base impedance of the system respectively. So normally, so V per unit is equal to, so V actual voltage, actual rating divided by V base. Okay, so actual rating is 345 kV divided by how much voltage? It is nothing but 300 kV. So by solving this, you will get 1.15 per unit. And second thing we need to find is base voltage. ZB is nothing but actual voltage divided, not actual voltage, so base voltage, no? So V base divided by I base. This is equal to, so 300 kV divided by 3000 amps. Okay, you will get 100 ohms. So 1.15 per unit and 100 ohms. And the suitable answer is option B here. And next question is, the surge impedance of 60 miles long underground cable is having 50 ohms. For 30 miles the length will be. Okay, the surge impedance loading. Surge impedance loading is independent of line length. So once it is fixed means it will remain as it is. So 50 ohms, it will remain as it is as a 50 ohms. Why? Because surge impedance loading is independent of length of the line. Next question. Next question here on the screen, the 21st question. A single core cable is designed to work for a single phase system with a peak voltage of 220 kV. So peak voltage of 220 kV. So V max is 220 kV maximum voltage. The maximum permissible stress in the dielectric is not exceeded 20 kilometers per millimeter. Okay, so the E value you can write, so E max should be equal to 20 kilovolts per millimeter. It should not be more than 20 kilovolts per millimeter. For economical size, so this is a given hint here, that is economical size, the overall diameter of the core. The general formula for this problem is, so E max or E is equal to, so V max divided by R, that is the radius of the conductor, into ln of d by r. For economic size of the conductor, economic size, this term ln of d by r is going to be 1, or d by r is going to be exponential power e here. Okay, so this is going to be 1 here, and E max is nothing but, so 20 kilovolts per millimeter is equal to 220 kilovolts by R here. So by solving this, R is nothing but 11 millimeter. In the given question, we need to find the diameter. So D is nothing but 2 times the radius. This is equal to, so 2 into 11 millimeters. This is nothing but 22 millimeters. Okay, and the suitable answer is option D here. And the last question for this session is, the stringing chart is used for. Okay, so normally the stringing chart is used for finding the sag in the conductors. So stringing chart is drawn like this. So here in x-axis we will take temperature here, and the y-axis we will have tension and sag. So tension and sag here. Okay, so this is the tension curve like this, and this is the sag curve. So this is the sag curve. As the temperature increases, sag will increase and tension will decrease. Thank you friends. If you like my videos, please subscribe my videos and like my videos. Thank you. Have a nice day. Bye bye.